Okay, so we're going to take a look at gases. So it's funny that we go from this idea of, okay, let's figure out molecular polarity and what that has to do with anything off to gases, because intermolecular forces, the topic that we're going to cover after this, chapter 10, and liquids and solids and all that stuff, that relates to polarity. Gases are completely different. That's why they have their own section. So gases have these characteristics that are unlike any other phase of matter. Liquids and solids they interact, those molecules interact with one another. And what type of molecule you have is incredibly important, and we're going to see why. But we always jump into gases separately because they don't behave like anything else. So this is kind of a short reprieve from all of the stuff that we're doing. We're going to get back into it. So characteristics of gases. So gases, again, are very special. They're very unique. They tend to, they have no constant volume. They will fill the volume, they'll expand to fill the volume of the container that they're in. So they will always fill the volume of the container, which is kind of crazy, because if you consider having container, there we go. Yeah, I can't spell today. If you consider the fact that if you had 3 molecules in the room, you're certainly currently sitting in 3 molecules of gas, they would literally fill the entire room. They would spread across the entire room. They would fill the container. There wouldn't be much anything in there, but it would be vacuum, but ultimately they would fill the space that you're actually in. Okay. So they fill the volume of the container. Because they fill up the entire container, because they're very far apart, one of the characteristics of gases, they are compressible. Compressible is an important part of this. That's why you see these large containers holding gas, because we can push those molecules closer and closer together, and therefore we can compress them, we can bring them close together. All gases are going to, because they're moving at a very rapid pace, that's the next thing, we know that gases are homogeneous. They're homogeneous, we consider them solutions. So these things are solutions. Gases mix constantly because they're moving at rapid paces, they're bumping into one another, and they're just mixing constantly. And then finally, let me just say that gases are ... Gases are constantly moving. And not only they're moving, but they are moving at incredibly fast speeds. Okay, so they have very fast velocity. They're very fast. They have high velocities. They're constantly moving. They're very far apart. It's important to mention that they're far apart just because the amount of gas in the room you're currently sitting in, or the room I'm currently sitting in, it could be compressed to a very small quantity. So gases take up a bunch of space. They also don't fill a lot of space, if that makes sense. So they're very far apart. The molecules themselves are very far apart. And the thing that really separates them, and that's why they need their separate chapter, is there are no intermolecular forces. And what that ultimately means is gas, and this is in an ideal circumstance. Ideal gases, there are no intermolecular forces. By the way, all gases are pretty much ideal gases. There's some special circumstances, and we'll talk about that in the last chapter, what makes something a real gas or a non-ideal gas. But ultimately, you have to get to very, very extreme pressures and temperatures to actually get there. So for all intents and purposes, everything is an ideal gas. So there are no intermolecular forces. Intermolecular forces, because we haven't talked about it yet, are basically just the interaction of molecules. Molecules aren't interacting. They're bumping into one another and heading off in opposite directions. That's about it. So let's talk about 9.1, gas pressure. So pressure is kind of the special thing for gases. Pressure is equal to force over unit area, some unit area. 1 atmosphere of pressure, okay, is equivalent to, when you say we're at 1 atmosphere of pressure, what is that exactly saying? Well, what that is saying is at sea level, it is literally the weight of the column of air, all of the weight of the entire atmosphere. That is the force of all of the air above you, right? One atmosphere. Force of weight of all air above you. It's literally the weight of the entire atmosphere directly above you. That is what we would consider one atmosphere, that force of gravity. For that 1 meter squared area, pushing down on you is the force that is equal to 1 atmosphere. It's a lot of weight, okay? So it's literally the space from me all the way up to space, the amount of stuff that is on top of me, the amount of air that is on top of me. But we can still stand, so it's kind of working out. The 1 atmosphere is equivalent to 10 to the 4th kilograms of air in that 1 meter squared area. So force, the amount of force exerted on our head per meter squared area. So atmospheric pressure is basically the force of pressure on you. And we have a barometer here. I'm just going to do a quick demonstration of what that actually is. So if I have a dish with some amount of mercury in it, okay, some amount of mercury inside of it, use gray. There's the gray. So that's mercury. Actually, I can just use this to do it. So we have essentially an entire container filled up with mercury. And you'll see in just a second why we use mercury. And then I attach a little capillary tube upside down there. Okay. The force of pressure of the atmosphere that is pushing down on the mercury is going to make it travel up into this container. So you have essentially mercury filling this whole thing up. Okay, so the distance, we have vacuum up here. This right here is going to be my mercury. This is mercury as well. It's the amount of essentially how high, the height of this from the surface is going to be the atmospheric pressure. So the higher the height equals the increase in pressure, as in the more it's pushing down, the higher that's going to go. And we measure that in millimeters of mercury. So that's where the term millimeters of mercury. So why do we use mercury if it seems like it's a scary thing? Because it does have to be exposed to air, right, in order to feel that pressure from the atmosphere above it. Well, the reason we use that is because this is a barometer right here. If we used water, the same atmospheric pressure would give us a millimeters or height of 33.9 feet of water versus using mercury, which is much heavier, much denser, which is 249 feet of mercury. So the height is an important part here, just in terms of able to read, creating an instrument that's going to measure it. So one more time, the pressure of 1 square inch of the entire atmosphere is equal to 14.7 pounds per square inch. So the amount of the column of air that sits on 1 square inch is 14.7 pounds. The amount of pressure on 1 meter squared area is 10.4 kilograms. That is what the idea of pressure is. Force per unit area. How much force is being applied per unit area? Okay, so we have a bunch of units for pressure. I'm going to highlight the important ones. So atmospheres is kind of the one that we're going to use pretty regularly. Atmospheres, we are going to use torr and the one below it, which is millimeters of mercury. Inches of mercury is one that's used in aviation. You're going to see bar and millibar used. You do see millibar and bar used occasionally in usually in meteorology. The IUPAC uses pascals, and kilopascals is obviously 1,000 of that. Pounds per square inch is not really used all that often, but you need to know these conversions. We have to be able to do these conversions. I'm not going to walk through a bunch of conversions because here are the units. You should be able to do conversions at this point in the class anyway. So the final thing that I want to talk about in this intro is absolute temperature scale. So when we're doing calculations, it's important that we use an absolute temperature scale. We have one. Absolute temperature scale is going to be Kelvin. What is absolute temperature scale? There is no negative value. So whenever we use a temperature when we're dealing with gases, we always have to use an absolute scale. So always, always, always use Kelvin. 1 Kelvin is equal to 1 degree C. So you should be able to do any conversions very easily. Again, that conversion is Kelvin is equal to degree C plus 273.15. So that's how you do the conversion if you have forgotten it at some point, but 273.15 or just 273. So again, the one we know well, 0 degrees C to 100 degrees C. Now I have 273 Kelvin to 373 Kelvin. Okay, and of course this goes all the way down to 0 Kelvin, which is absolute zero, making negative 273 degrees C equivalent to absolute zero. So again, one more time, we just have to use Kelvin when we're doing any of these calculations, because negative numbers are going to screw things up for a variety of reasons, because we're going to be dealing with a lot of ratios. Negative numbers and ratios don't behave well. So please make sure you use an absolute temperature scale every single time. Okay, so this is one really quick primer to pressures. Please kind of look through a barometer. If you want to read through your book and get some more context to this stuff, go for it. But you should be able to do all of these conversions, particularly atmospheres, torr, and millimeters of mercury. By the way, millimeters of mercury, one more time, 1 atmosphere is equal to 760 torr or millimeters of mercury. They're actually the same exact scale. So 760 millimeters of mercury or torr. Okay, so again, just be able to do that. And then pascals, by the way, I guess I'll just throw this in too. 101,325 pascals, which is equal to 101 kilopascals, or 101.325 kilopascals. But again, you get that is kind of the most important thing, is being able to do conversions for all of these pressure units and using absolute temperature scale. So that's that.